Hello. Today we study part 2 of chapter 14, hypothesis testing and confidence intervals related to the simple linear regression model. We start with the population model assumption. Recall the population model has the form yi equal to beta 0 plus beta 1 times xi plus epsilon. We want to study the linear relationship between x and y by taking the expected value of yi, which is expected value of yi equal to beta 0 plus beta 1 times xi, where beta 0 and beta 1 are the parameters. Moreover, beta 0 is the true y-intercept and beta 1 is the true slope, and epsilon is the random error in y assumed to be normally distributed with the expected value of epsilon equal to 0 and the variance of epsilon equals to sigma square. There are two important notes I would like to mention. Note number 1, mean square error S square equal to MSE is equal to SSE over n minus 2 is the estimate of sigma square, which is the variance of the error term epsilon, and S is equal to the square root of MSE or the square root of SSE over n minus 2, which is the estimate of sigma, the standard deviation of the error term epsilon. The next topic involves the hypothesis testing with the so-called 3-step procedure that we will use for the testing. Testing for significance. We used t-test for the true slope beta 1 to determine the existence of a significant linear relationship between s and y. Step number 1, just like what we had done before, state h0 versus h1. And h1 is our claim. We used beta 1 not equals to 0 to establish a significant linear relationship between x and y. And the keyword is not equal, so we have a two-tailed test. Step number 2, we need to compute the test statistic, and for computing the test statistic, we use this equation 14.19, and this t-cal is equal to b1 over sb1, and this is a t-test, so we need to find the degrees of freedom. In this case, the degrees of freedom will be n minus 2. Now, this b1 is the sample slope, and sb1 is the standard deviation of b1. So to find this standard deviation of b1 sb1, we use this equation 14.18, which is equal to s over the square root of the total sum of square with respect to x value, and this value will be given. So it's the sum of si minus s bar square. Now, from equation 14.16, we'll be able to find this s, and this s is equal to square root of SSE over n minus 2. And then step number 3, make a decision using either the p-value approach or the critical value approach. Now, by using the p-value approach, keep in mind we have a two-tailed test, and also the t-table, we do not have all the value for the probability, so we need to find the probability range. And in this case, the p-value is equal to 2 times the probability range, and you will use the t-table with degrees of freedom of n minus 2 to find it. And we reject a 0 if the p-value is less than or equals to alpha. Now, for the critical value method, keep in mind we have a two-tailed test, so the critical value will be t's of alpha over 2, and the degrees of freedom is n minus 2. So after using the t-table to find the critical value, we draw a normal line, put the 0 in the middle, and the critical value is either t's of alpha over 2 or negative t's of alpha over 2. And our rejection region is on our tail. That is, we reject a 0 if the test statistic is more than your critical value on the right, or your test statistic is less than your critical value on the left. And if it's in between, we fail to reject H0. Now, let us look at this example. Example number 3, giving SSR equal to 27.51, SST equals to 41.27, the total sum squared with respect to x value sum of xi minus s bar square equal to 18.38, and the regression equation yi hat equal to 3.0 plus 0.5 xi, which give us b0 equal to 3 and b1 equal to 0.5, and n equals to 20. Use the t-test to test the existence of a linear relationship between x and y with the level of significant alpha equals to 0.05. Again, we are going to use this 3-step procedure to do our hypothesis testing. State H0 and H1 is our step number 1. So we use the claim on H1, which is beta 1 not equal to 0, to establish a significant linear relationship between x and y. And H0, beta 1 equals to 0. And notice this is a two-tailed test. Step number 2, compute the test statistic. Now, we have this sub-step number 1, find the standard error of estimate S. This is from equation 14.16. Okay. You have S equal to square root of SSE over n minus 2, which is equal to the square root of SST minus SSR over n minus 2, and SST is equal to 41.27, SSR is 27.51, and n is 20, so you have the square root of 41.27 minus 27.51 over 20 minus 2. Using your calculator, you'll be able to get this value 0.874. And then sub-step number 2, you're going to find the standard deviation of B1, and this we use this equation 14.18, and this is equal to S over square root of the sum of square with respect to x value, which is 18.13. So you have 0.874 over square root of 18.38, which is equal to 0.204. Now, sub-step number 3, we're going to find the test statistic tcal, which is from equation 14.19. and this is B1 over SB1, and B1 is 0.5, SB1 is 0.204, and we get this test statistic to be 2.451. And then step number 3, make a decision. In here, we will use the critical value method. So keep in mind, this is a two-tailed test, and alpha is 0.05, so alpha over 2 is 0.025. And the degrees of freedom will be n minus 2. N is 20, so degrees of freedom will be 18. Now, using the t-table, we'll be able to find the critical value to be 2.1009. So we draw a number line, put the 0 in the middle, and then our critical value will be 2.1009 and negative 2.1009. Now, the test statistic is 2.451, which is more than your critical value on the right, so we reject a 0 and conclude that there is enough evidence to say that there is a significant linear relationship between x and y. We can also use f-test for significance in simple linear regression model. So step number 1, again, we state h0 versus h1, and this h1 is beta 1 not equal to 0 versus h0 beta 1 equals to 0. And then step number 2, we will compute the test statistic. And we use this equation 14.20 to find the mean square regression, which is MSR. This is equal to SSR over the number of independent variables, or you said the number of x's. In this case, x is 1. And then from equation 14.21, the test statistics for f-test will be MSR over MSE. Now, for the f-test, we use the critical value method to make a decision, and for the f-test, we have a right-tailed test. So we reject a 0 if the test statistic f is greater than or equal to f of alpha, and this f of alpha is the critical value, and it's a right-tailed test. Now, we will study the confidence interval estimation related to the simple linear regression model. The first one on the list is the 101 minus alpha % confidence interval for the true slope beta 1. Again, we will have the form of point estimate plus or minus margin of error. And in this case, we use B1 to estimate beta 1, and this is our point estimate B1 plus or minus the critical value T's of alpha over 2 times the standard deviation of B1. And this is the equation we will use to find the confidence interval for the true slope beta 1. And let's see, our example number 3 is the continuation. Find the 95% confidence interval for the true slope beta 1. And this is a 101 minus alpha % equals to 95%. We cancel out this 100 and the percentage to get 1 minus alpha equal to 0.95. So alpha equal to 0.05 and alpha over 2 equal to 0.025. And the degrees of freedom is n minus 2, in which case is 18. So from a t-table, this t is 0.025 is equal to 2.1009 from the previous slide. So B1 plus or minus T's of alpha over 2 times SB1 is equal to 0.5 plus or minus 2.1009 times 0.204 from this example number 3. And use your calculator. You'll be able to get the lower limit to be 0.071 and the upper limit to be 0.929. So we are 95% confident that the true slope is between 0.071 and 0.929. We don't know where is the true slope, but we know it's between the lower limit and the upper limit. And how sure we are? 95% sure. Next, we consider this 101 minus alpha percent confidence interval for the mean value of y for a given value of x. And we use this equation 14.24 to find the confidence interval. So this is y hat star, and this is the predictive value of y for a given value of x, and then plus or minus the critical value T's of alpha over 2 times the standard deviation of y hat star, where we'll be able to find this s y hat star by using equation 14.23. And this y hat star, sy hat star is equal to s times the square root of 1 over n plus this x value at a point minus the mean x bar and square over the sum of square with respect to the random variable x. So the sum of xi minus x bar square. And let's see this example. Example number 4. To study the relationship between the size of a store X, the unit is in 1,000 square feet, and its annual sales Y, the unit is in million. We randomly selected 14 stores and obtained the following information. Y hat equal to 0.964 plus 1.67 times x. So you have B0 equals to 0.964 and B1 is 1.67. And we also have SST equals to 116.95, SSR equals to 105.75, and the total sum of square with respect to x is the sum of xi minus x bar square, which is 37.924, and I ask you to obtain a 95% confidence interval of the average annual sales for a store that is 4,000 square feet, with this mean equals to 2.921. So we are going to use those two equations to solve the problem. And first of all, the unit for x is in thousands. So when you do the calculation for the predicted value of y for a given value of x, you need to use x equals to 4. Now, next, we need to find the critical value T's of alpha over 2 using the T table. And we also need to use this equation 14.23 to compute the standard deviation of y hat star. And we need to find x. and we need to find the square root of 1 over n, and this n is 14, and we need to find this value. So you have x star to be 4, and then this x bar is 2.921, and then the denominator, this sum, total sum square with respect to x, will be 37.924. We are going to solve the problem. We are going to solve the problem using the following steps. Step number 1, find y hat star. For x equals to 4, this y hat star is equal to b0 plus b1x. So it's 0.964 plus 1.67 times 4, which is 7.644. Next, we find the standard error of estimate s, and which is equal to square root of SSE over n minus 2, which is SST minus SSR over n minus 2, which equals to 116.95 minus 105.75 over 14 minus 2. And that will give us this value, 0.966. To find the critical value, t's of alpha over 2, we need to use n minus 2 degrees of freedom, in which case this is 14 minus 2, which is 12. And using the t table, we'll be able to find this value, 2.1788. Now, we need to find the confidence interval. So you have y hat star, which is 7.644, plus or minus the critical value, 2.1788, times s, which is 0.966, times the square root of 1 over n, which is 1 over 14, plus x star, which is 4, minus x bar, which is 2.921, and square it over the denominator, which is 37.924. And using your calculator, you'll be able to find this value, 0.673. So the confidence interval for this example will be 6.971 as the low limit, 8.317 as the upper limit. And here's the concluding remark. We are 95% sure that a store of 4,000 square feet will have an annual sales of 6.971 to 8.317 million. The last topic is how to read Excel computer output for the simple regression model. Giving a set of data, and we can enter the data into the Excel and obtain this simple linear regression model. So we have this Excel output, and now we need to know how to read this Excel output data. And you have this coefficient, 0.964, 1.670. So this will be our B0, and this will be our B1. And then this is standard error, and this is SB0, and this will be SB1, or the standard deviation for B0 and standard deviation for B1. Now, this t-test will be our test statistic. So for this beta 1, when we do our hypothesis testing, and this will be our t-count. So it's 10.641, and this is for our y-intercept, and this is 1.831. 2. And this is the p-value associated with our hypothesis testing. And for testing for beta 1, and you're going to have this 1.267 e to negative 7. This is a scientific notation for 1.267 times 10 to the minus 7, and literally 0. Now, this lower 95% and upper 95% is referring to this 101 minus alpha percent confidence interval for the true slope and the true y-intercept. Okay, so this is the confidence interval. This is the end of chapter 14.